He's professor at the Universidad Técnica Federico Santa Maria de Valparaiso in Chile. So Mauricio has done his PhD in France, astronomical data. So from closer and closer from astronomy, and it's a real pleasure to have him here today. And he also worked on side projects like data analysis of cloud services based on Docker and stuff like that, and also Jupyter Astronomical libraries, which are common tools to share methods and tools to analyze data. So today he's going to talk about structure characterization and compact representation. Thank you.
Okay. Thank you. Okay. So I'm a computer scientist, so probably I will make mistakes about astronomy, so be patient with me. Also, I speak French, so I can answer questions in French, and you can ask in French if you want, okay? I will talk about structure characterization and compact representations in astronomical hyperspectral images or in cubes of data. But first, I want to give you a little bit introduction about me that already Philip told, and a little bit on the projects that I am working. So I'm an assistant professor since January of this year in an electronics department in Santa Maria, and I am part of the several centers, including the Telescope Consortium and the Pattern Recognition Association in Chile. And my research areas are data science, machine learning, artificial intelligence, and astroinformatics and astroengineering as an application of these techniques, including applying all this to distributed systems and large data systems, and specifically in more what I do in theoretical research in computer science is reinforcement learning, micro decision processes, and information theory and the theory complexity in general. I have some EC Scopus articles and a lot of small ADS NASA articles like the ones you can present in ADAS or things like that to this point. So my formation is just computer science, so both in the master's and the PhD. But I have been involved in astronomy research for already more than 10 years, 14 years I think. So I will like to introduce you basically the research lines that are in different colors, but today we will talk about these ones. So here in blue we can see the research on infrastructure that we have done for the Chilean Virtual Observatory. That means basically picking the standards and architecture that the IVOA produces with the stuff that it's for the Chilean Virtual Observatory in order to publish ALMA data and other data generated in Chile in a standard format using the VO standards. Due to the same reason, we have to manage infrastructure, so we have a couple of supercomputers that we have to manage and make all the infrastructure in order to work and put everything together with cloud systems right now and put an infrastructure that can be used for research. And in the same line, we have like the Jupyter notebooks running online that can be used for high performance computing to do things like this, which is processing the whole a whole data set of a lot of ALMA fixed cubes and to produce basic statistics about them. So it's processing a lot of terabytes of information to produce this. Okay. So this is like the research in the infrastructure area. I also work in time domain, like what is very popular in machine learning for astronomy. It's to work with time series and specifically with light curves. And we're working here in trying to find this is this is the period of a variable star, and here we have the intensity. So we're trying to see what happens in the long period, like several years, 10 years, and see which are the different types of variability on the stars that are there. And we want a machine to tell us which is the clustering, which are the different types of variability that we find in stars with long periods. Other project is picking the Kepler data to finding exoplanets and use a machine learning algorithm which is very known right now, which are convolutional neural networks, in order to obtain from directly the observations the same parameters that astronomers have obtained by hand, and try to replicate this in order to apply these algorithms to other datasets that are not the Kepler database. We also are trying to make clusters of different stars that have a variability on the whole spectra and try to characterize that. It's a much more newer project. So all of these are in the time domain. So today I want to talk to you about this other domain, which is basically structure detection and region of interest detection. And what I want to talk here is a few contributions that we have made in this line. For instance, this is for region of interest detection, similar to Sextractor, but using a multi-scale representation. The same idea, a little bit more advanced with wavelets. The representations that put me in contact with here, which is the bubble clamps representation. I will talk a little bit more about this, and a much more recent work in representations. So first, I guess everybody knows this, but here we're talking about hyperspectral images or data cubes that has retranslation declination and also velocity or in general frequencies. Yeah. So we have several channels of frequencies. I work with data obtained from the ALMA Observatory, even though all the techniques could be applied to any radio interferometer, or actually going to other wavelengths. But for me as a computer scientist, I see the same cube just as a solid cube of intensities, okay, and a three-dimensional array of intensities. So I try to use this idea to work with data. The first thing that I want to explain is a little bit how I assess the results that I have. Even though in the papers I try to use real data, internally I try to use just synthetic data to verify if what I'm doing gives the correct answer before trying with real data. For that, I built a simulator that's called ASDO, or a synthetic data generator that pick emission lines from Splatalog or any molecular database, and generates basically using certain model for the emission lines, the local radio velocity gradients, some corrections due to the redshift, and some broadening functions. We try to represent simple structures like a couple of Gaussians, a couple of circles, as a synthetic model in order to compare them with what we obtain as a detection. So we generate the functions in order to test them later. So we can have a Gaussian line profile like this one, and what this simulator do is to basically factorize the intensity maps as certain functions, the local molecular redshift maps, and the broadening maps. So with that, we produce from a concept of a universe and then a concept of a telescope, we produce this type of results similar to what a FITS ALMA file looks like. Okay, so the idea here is basically produce the spectral lines and then putting that into certain functions that looks like this in each slice, and then with that we produce this data here. And as we know the specific lines and the specific structure, we can recover the same structure and see if the algorithms work correctly. Okay, so let's talk about these 4 contributions that we have made. Well, this contribution was a small contribution in an ADAS conference in 2014, but it has been very useful to assess my results. Okay, so let's start with the region of interest. The first thing that we have tried is to say, let's try to reduce the dimensionality of what we are observing by selecting a region of interest. And for that, we built up a pipeline that makes some spectral processing by using morphological operators and try to get a sketch probabilistically of the spectral lines, yeah, of the broadening. And with that, we have estimation in the velocity where the signal is. And with that, we stack all these slices and then do a multi-scale segmentation using morphological operators. What is that? It's basically, so yeah, I have support for this. So we do the spectral processing by trying to get a sample of this and get when this curve gets saturated, and then we said that this is enough. So we select a few slices and then do the spectral field extraction to know which is the velocity field that we are working on, and then we make a multi-scale segmentation by picking like squares here and apply a few morphological operators that convert all these square into one single value. And if you do that for several different scales, here you have small detections or large detections. And with that, we make an object indexing. So we pick each object and try to see if this object is in the same pixels as the larger one. And if it's in the same pixel as the larger one, we say that it's the same object. Okay. If not, then it's a different object. And this way, we can have different sizes, different scales, and a connected version of this detection at different levels. And this allows you to go inside and see how it works. Okay. And the good thing is that this is not a very advanced algorithm. It is a very basic algorithm. And that is a good thing because we can divide this automatically by just putting the code in a program and run this for instance, all the fit files of cycle 0 and 1, I think it was, at the same time, in order to put it in a supercomputer and compute this region of interest for all the ALMA data set. So we're talking about several terabytes of data that we have to process. And we cannot see it very good, but here we have like the different values for each of the region of interest. So you have central right ascension, declination, get major axis length, minor axis length, the area, the eccentricity, the solidity, etc. Okay. So the good thing is that we end up from terabytes of data with a catalog that tells me where the signals of each ALMA fit file is. Okay, so we can end up with things like this, where here you have the area of the region of interest, and here you have the intensity in Jamski Berlin, and here you have all the observations of ALMA, and it looks that way. I'm not an astronomer, so I do not know why this have this form and why you have these large intensities here in large areas separated, but it's interesting to see that this is the values that have been observed in ALMA. And here you have the whole sky, radioastronomy declination, and here you have the intensity of each observation. So you can see probably something like the Milky Way here. Okay, as I told before, we did all this in Jupyter Notebooks in a data center, so we can see that this is a more friendly way to move the processing and analysis where the data is in the data center and not in the astronomy computer. Yeah, and that's one of the side projects that we have. Another different way of looking this same problem is to do the multi-scale analysis using the mathematical tools that are available, like wavelet decomposition. Wavelet decomposition, for those that do not know, it's like similar to the Fourier decomposition, but here you have a certain scale that moves. So it's for non-stationary signals. You have Fourier decomposition for stationary signals that works very well. It can decompose any signal for decomposition, but a wavelet decomposition is more tailored for non-stationary signals. So in case of astronomy, you have a star or whatever, or extended source, it looks much more like a non-stationary signal. So we use the discrete wavelet transform to produce different scale representations of the same elements. And with that, we use a known algorithm for finding clumps in molecular clouds, like clump find, and we try to contour the detection at each level. And this work, unfortunately, ended up just working in 2 dimensions because, unfortunately, the student passed away, so we did not finish this work. But we pick his ideas and continue in other work that I will show. So this is basically the first part, which is just working with pixels. There is no very novel thing in this idea, but was our introduction to the field. I want to talk much more in detail about this representation that it's called bubble clumps. So if you see the work that has been done for detecting structure in molecular clouds or even in galaxies, you will see things like clumping algorithms, trying to detecting clumps in not only just in an image, but in the data queue. And you may generate the region of interest, but you want to generate also velocity maps and probably tables of clumps to make catalogs. And I've just realized when I've seen the algorithms that this is very similar to what in machine learning we call clustering. But it's not exactly the same. So the question is how we can apply clustering algorithms to this problem. And for that, if we see the clumping methods are more popular, now there is another one that's called CPROP. We have the ancient Gauss clamp that basically assume that each clamp is has a Gaussian shape, and this is a strong assumption. Yeah? So it works fine if you know that your clamps have a Gaussian shape, and it's, I think, always not the case. Clamp find works in terms of pixels. So you just try to separate things by putting a threshold and going down in the algorithm. And when you see that you have different values, then you open a new clamp and then you separate things in this way. But you do it in 3 dimensions. And this algorithm is very sensitive to parameters, but it's very used, at least in molecular clouds. That's what I've seen. And the problem is that it assigns one pixel to one clump, and it's very topological on the structure, and it doesn't get any fractal representations or any hierarchical representations of the data. So a completely different algorithm was dendrograms, like 10 years ago, where the idea now is to represent like the peaks of the data and connect them in order to produce different groups that are hierarchically connected and not only like topologically corrected. So you can understand more how things evolve or has been generated with algorithms like dendrograms. And we have much more heuristic ways to do this, also faster way like Feldwalker, which is an algorithm that actually use gradient descent or hill climbing, as you want to present it, in order to generate a separate group similar to ClambFind. It's a little bit more robust than ClambFind, but I think it hasn't get the attention that it needs. It's a quite good algorithm, but not very popular. So Gauss-Clam, in my opinion, is well motivated, but the problem is that it's too complex. Has too many parameters. I think it's more than 32 parameters to tune up, and they do not translate to physics at all. All the parameters have algorithmic choices that you have to make, so it's difficult to tune. And it's good to make some region of interest selection, and may be good for estimations if your clumps are actually Gaussian, but it's not a simple algorithm. ClambFind, on the other way, it's simple, no model behind. Feldwalker, for instance, is not as simple as ClambFind, but the problem is that only selects the region of interest. Then you have to check this region of interest if you want to estimate the flux or estimate whatever you want, the velocity or the gradient. Dendrofind is hierarchical, but again has no model. It's not very flexible. You just put whatever the parameters are, and it's not allow you to make different sign cases for this, and also do not allow you to get estimation. So the idea was to try to pick the best ideas of each one and put it together a new algorithm. The first thing that we have tried is to use the same idea of using wavelets, but now in order to make an estimation. So we build up a mother wavelet in 3 dimensions that allow us to estimate the different parts of in multi-scale analysis, the different parts of a molecular cloud, and try to get the connections between large-scale structures with small-scale structures. Okay. These have a few results, but we abandoned that because the wavelet transformation was too expensive. It was a slow algorithm, and it was not very easy to interpret. Has not very good extensibility. So we tried to simplify our model, and we ended up with this bubble clumps idea. This idea is very simple. We can approximate a cube where x are the 3 coordinates here, with a set of parameters plus a Gaussian noise. We assume that the noise is Gaussian here, and then we can approximate that with a series of continuous functions where each function is the same. So we call that a kernel, and the kernel must have certain properties, yeah, like being between 0 and 1 and other mathematical properties. And we put here a parameter which is the size of this kernel, which is the intensity, let's say, of each one of these functions. And we started with a very simple idea. It's just consider that this alpha is constant for every value. Okay, one might say this is a very bad idea, but actually it gets very interesting. As we have here certain error, certain noise that it's modeled as a Gaussian, we can construct this as a typical maximum likelihood optimization problem, and we end up with the least squared problem between basically the real cube and our estimation, but constrained to certain characteristics. And in this case, what we want is to estimate the flux always below the real value that we can find in the pixels. And this is very important because if you leave these functions alone, then you will have not real flux in our estimations. Okay, so we always underestimate the flux in this representation. And this can be obtained by updating an energy matrix that allows you to subtract this, let's say, bubbles, which is these Gaussians that have the same structure, and we have an algorithm here in order to update this energy efficiently. So we iteratively get with this other algorithm all the small Gaussians from here in order to end up with a representation like this. Okay, so each Gaussian there, each function that could be any function, but let's say Gaussian, represent part of the cube, not in the pixel domain, but in the continuous domain, and each one of these ones are equal. Okay. The good thing about being equal is that it can be interpreted as a independent and identically distributed sample of the image. So this representation, it's like sampling the image, but each sample is independent and each sample is identically distributed. And that's the major requirement of machine learning algorithms in order to be applied. So, as I've said, we have a few theorems on how this error will be bounded, but we can select a function that makes this bound much more, much lower, and these are basically Gaussian functions. So we end up with Gaussian functions with a compact support. Okay, so let's go to data. This was too theoretical to this point. Here we have 4 cubes from the ALMA Science verification data set, which are small cubes. So we have a few hundred pixels for each rate translation declination frequencies and dimensions, and for the frequencies we have at most 500. Okay, but this means that we have this amount of pixels to store, and here other data like the angular resolution, the beam size resolution, etc. Okay, we have selected these 4 cubes, which are Orion, M100, Grand Design Galaxy. Here we have a protoplanetary disk and a binary system. Okay, so this algorithm that I have shown you needs an estimation of the signal to noise ratio, and for that we pick the RMS and try to find the point where if you cut a different RMS multipliers, then if you cut the image there, then you will start having a lot of noise first, and in some point this will have this inflection point. This is the derivative, some inflection point, and you will pass to the signal. So this point is an heuristic for finding where you do not have where the signal begins to mix with the noise, if you want. Okay. And with this, we have this new representation. So this is the original image stacked. And here we have our representation. And here we have the residual. You might think that the residual is not very good, but we can filter the error that it's produced over here, because we have overestimated the values over here later, as we will see. Okay, so we have explained a little bit how this works, how much time I have, yeah. But we haven't talked about why we want to try to do this. And the basic idea of this is try to compact this huge cube of data into a much more simpler representation that can be used for analysis. So here is the concept that you might compress a cube, in a zip file in order to bring it to your home. But that card is completely useless in this point. Yeah? A compressed card is completely useless. What we are trying to do here is a compact representation, not a compressed representation, which is the same functionality like a car, like a larger car, but in a small way that it's not the same. You will have not the same power as the original car, so you will not have the same power that the original data, but it could be used to make some simple analysis, at least. Okay. So here, if you see, we have a representation using this algorithm that it's for this image 1.7% of the original size that we have, and these other ones that are much more condensed signals, we can see that we have 0.1% of the size and 0.3% of the size. So we can produce in a reasonable time, this is a couple of minutes, in a reasonable time we can obtain a good representation that will be useful for analysis, that can be applied machine algorithms over it, and that actually looks like it has the content itself, which is this one over here. So let's look a few ideas. So, here is the spectrum. Yeah. So remember that this is a cube, so we can obtain here the spectra of the line, of 0, 1, 0. And you can see that the spectra here can represent a little bit the content. Okay. So let's talk a bit about what are the applications of this representation. For instance, here we have a vertical decomposition of equal flux to each of these images. So we picked this original image, we have this compact representation of 1.7% of the original size, and then we just pick the top one Gaussians, the top one element, and produce this image. And this image have the same flux that this other image, but a little bit more distributed. So if you sum all of these images, you will produce exactly the same function. This is very easy to do with this representation. That's what I call a vertical decomposition. Well, it might be used for science, I'm not sure how, but it's just to show that it is, you can do that, okay? So, but let's go to learning. What you can do also with the representation is to actually apply clustering algorithms. In machine learning, you have several clustering algorithms like K-means, DB-scan, hierarchical clustering, agglomerative clustering, and these are very good algorithms. In this case, we have spectral clustering, which is one of the most expensive algorithms, but due to the low dimensionality of the representation, you can produce this type of clustering. So what's the main difference between a normal clump detection from this clustering. The first thing is that you can see that clusters are overlapped. Usually, in pixel-based algorithms like clump find, you assign one pixel to one clump. Here, as you can do this vertical decomposition, you can assign a few of the bubbles to one cluster and a few of the bubbles to the other, and that allows you to represent blended sources or blended emission. Okay, if it's a good separation or not will depends on the science goals that you have and also the parameters that you use. But the thing is that this representation allows you to use these algorithms and produce this kind of results. Let's see the case of the protoplanetary disk. Here, as I said before, we produce here representation that, if you see here, has a lot of different clusters. So we have a main cluster that it's actually the disk, and a lot of, let's say, noise. So you can clusterize this actually using mean shift clustering, another algorithm that you can select. It could be k-means or it could be dbscan, it doesn't matter in this case. And we just say that everything that it's not this huge one, it's basically noise. So it's noise that we pass from the original data to this representation. So now we can filter this and just keep this this single structure. Here we have the structure in radioastronomy declination, and in the other dimension here and then the other dimension here we have frequency. So you can see, sorry, in the other dimension here and here. So you can see that the velocity goes the two ways from the center. Okay. And later, just selecting these groups over here, just the purple one, we can make something like a self-organizing map, which is machine learning neural network algorithm that allows you to learn the manifold where this data lives. So basically here, with a few neurons, with a few points, we are representing with this mesh the structure in terms of velocity and radioastronomy declination in a single image with only a few points here, but they are connected. Okay, so this could be useful to knowing how the structure of the disk is working. Other idea is, for instance, galaxy morphology. We can pick this M100 galaxy, do some cleaning similar to the other idea. We just make a clustering of several of these Gaussian functions, and then keep only those that look like arms, and then separate this into different parts. Okay, and here you have the predictions for the frequency. So remember this. Always, it's a cube. This is not an image. And then we can have this gravity schematic where we represent for each one of these clusters just the total flux, which is the size of this point, the radial velocity, which is the color. So if you have a cold color, then it's going, relatively to the center. It's a negative velocity, let's say, and here you have a positive velocity. Yeah. So we can see that this galaxy, these points are going far away, and this goes near away for us. So we can estimate how this is going. And these lines are like, let's say, the gravity between them. It's just to connect the points depending on their values. And you can use this very, very low representation, which is just points with a certain estimation of the intensity of the mass that you have in here, and the velocity, in order to feed up an n-body simulation, for instance, and start a simulation from real data. Initialize a simulation from real data. Another application, it's source detection and light detection. Yeah? Here you have, again, these two sources, and you might want to cluster things, but now if you see, the clusters are not in the space, but more in the focus in the velocities. So then you can separate the both sources and try to match each one of these lines with a spectral line, yeah? In order to know the composition of and the abundance of each of the elements that have these sources. The good thing about this is that then you can do use data fusion algorithms like this, which is a moment preserving algorithm, in order to produce a catalog of the different lines that you find. So here you can see where they are in the right translation and declination, but where they are in frequency, and also having not only the lines, but the shape of the line, okay, in the space. So you have the major semi-axis, the minor semi-axis, the angle which is rotated here, the full width that have maximum, and actually the gradient of the velocity in terms of the space. Okay, so you can obtain all this information just from this clustering. Okay, so that was this idea. I didn't show, but we will have other clustering that is possible. A much more recent contribution was the HDM cloud, which is a specific algorithm for molecular clouds, but I think it can be applied to other things also. Okay. Well, this paper, sorry, it was presented in. It is published in Astronomy and Computing, and this paper is presented in MRAS. Okay. So the Gaussian mixture reduction idea is that we will try right now to not assuming that each Gaussian that we will subtract from the signal is of the same size, but we will construct an optimization problem for this. So for that we select some points. It gets quite large to explain how you can select these points, but the basic idea is to have an homogeneous representation, but weighted by the flux. So we have all these points, which are the center points of the Gaussians that we will use. You have some collocation points, which are the points where we will evaluate the quality of our representation, and some boundary points that will tell us which are the limits of our optimization. And with that, we have a variational approach which minimizes the difference. Basically, it maximizes the similarity between the real data and our model, but also have some domain constraints, like not having more flux than the original image, and a few other positivity constraints. And what we do here is basically assuming, again, that we have a Gaussian function, but with an almost arbitrary covariance, and obviously any position that we want, and also not the same weight for every Gaussian, but a different weight for each one. And with that, we can optimize using normal nonlinear optimization algorithms, based most of them on the Newton method, like Leverman-Marquardt, for instance. And we generate synthetic data and try to see how these Gaussians look like in our reconstruction of the elements. Okay, so how this representation works. We have a lot of Gaussians after the optimization, but they are not connected at all. And each Gaussian do not represent anything. It does not represent a source, any physical quantity. It's just a representation of the cube that we have. Then to give some representation, what we do is to do something similar to what hierarchical clustering does, which is having a measure for comparing these Gaussians, and if they are similar, then we put it together in a new Gaussian. Okay, so we agglomerate things based on the similarity of the moments. As there are Gaussians, we compare the mixed Gaussian compared to the sum of the two other Gaussians, which are here, and that way we can produce a new Gaussian with different weight, different mean value, and different covariance metrics, and we compare them to see how they work. And we do that iteratively to produce this hierarchy of elements. So in the end, we end up with these same Gaussians that are, here we have plotted the limits of these Gaussians, the curve level, I think in English, yeah, the curve level. And the good thing about this is that we can cut this whether we want. So here we have the original one, and here we have cut this here in two. Okay, so here we have cut this in two. Now we have a blue one and a red one. Okay, this is a schematic. Obviously, this amount of Gaussians are much more. You have thousands of Gaussians, but you can start dividing your structure in different groups. And here, for instance, you have, I don't know if you can see it correctly, but you have overlapped also structures. So again, going to continuous functions allows you to have overlap clumps that allows you to represent more, in my opinion, what the physical properties of these clumps are, and not only the pixel-based separation that previous algorithms provide. So here, as you can see, here is the result for the clump find, and here is the result from the Feldwalker algorithm. So here we said, okay, this is a clump rather than this one, and it's a little bit overlap with this one. So that do not make this sharp structure here that probably do not exist at all. Okay, we have a much more continuous representation. And again, this representation is very fast to divide. So again, you can, if you are not happy with this, for instance, separation, you can, let's say, double click this and it will divide it again in two groups. I think this tool will be very useful for making things more closer to what astronomy is, which is analysis. An algorithm like clump find just gives you an answer, and then if you want to have a different answer to see what is happening, you have to run the algorithm again. This representation, these hierarchical representations allow you to get different representation just by cutting the tree in different parts, similar to what dendrograms do. Okay. These examples were in 2 dimensions. If you go with the spectral domain, also you can do this. And then the separation depends a lot on where the velocity is. So you can find certain structures that have different spectrum than the other, and that's why they are separated. So this allows you to separate again, not only by the spatial coordinates, but also the spectral coordinates. Okay, so these are the research lines that I want to explain a little bit today. So acido, the region of interest detection, and this structure detection. I just want to talk about very shortly about these new projects that are like the new stuff that I'm working. I'm working with the CTA Observatoire in gamma reconstruction, which is basically trying to, from the images that the atmospheric telescopes, how I don't remember, welcome to the imaging atmospheric telescopes of Cherenkov, the Cherenkov effect produces. You can take the light from here and try to predict where the gamma ray came from, and actually try to know if it's a gamma ray or another thing, and a hadron, a muon, etc. So what we are using here is again deep learning neural networks in order to produce a stereoscopic or several telescope prediction of where the gamma ray is in terms of right ascension and declination, and the energy of the gamma ray. Other things that we are doing is continuous synthesis, which is basically using continuous functions rather than the fast Fourier transform to pass from the UV plane to images. So it's basically another way of doing synthesis. And what we present next week in ADAS, it's content-aware search, which is basically not having only the virtual observatory to give you the metadata that someone has written in the data that you are searching, but also going deep into the data itself in order to select certain number of, I don't know, flags window that you want, or some other characteristics that are not in the metadata but are directly on the content of the image. So that's basically what it have. I have obviously a lot of other backup slides, but probably I haven't explained everything very correctly, so I'm open to a lot of questions, because I think that this is quite different from the field that you are used to. So.
Thank you, Mauricio, for this overview of all the different projects. You have questions?
Thank you. So I have a simple question that I ask myself since a long time, so maybe you have a simple answer. When you try to look into interferometric data like ALMA data, why do you work on the images and not directly on the visibilities? What is the advantage of using the reconstructed image, which is full of approximations, rather than working directly on the visibility data set, which is the Fourier?
Yeah, I completely agree with you. The fast Fourier transform and then the clean algorithm adds a lot of artifacts that are not really there. Okay, so the main question that I ask to you is which algorithm or which method you will use in the visibility. So that's the point. We have a lot of algorithms for images. As you see, ClamFind, for instance, for detecting this, it's basically a segmentation algorithm that it's well studied, and we know which are the results. If you go to segment things directly in visibilities, that will give you basically the range of frequencies that you know, but know the position. So it's difficult to work over there, I think. How you can select the source that you want if you have two sources, for instance.
Well, you can make a model of two sources in the visibility and fit that. Actually, we do that already, like when we have visibility data, sometimes we make like Gaussian models, or just, and then we just Fourier transform it and we compare it to the visibilities, and of course it's an iterative process. So I wonder, is there a good reason when you want to do this kind of algorithm to look for sources, why to work in the images? Because I think you can take a sky, a synthetic sky, and make visibility.
It's exactly the bottom line between that. I haven't said it, but the bottom line here of this whole presentation is that I want to move the fitting process, where you want to fit something in order to put in your paper, the fitting process into continuous functions as early as possible. So it's basically, yes, my idea of working in this continuous synthesis to try to make the fitting into continuous functions as early as possible in the visibilities, and then make all the analysis in this world and not in the pixel-based world. It's prone to a lot of systematic errors that are added. So yes, I think it's because it's more difficult to work. You have less tools to work in visibilities, but I think it's the way that we should go.
The problem is also much larger with visibilities. Like orders of magnitude. The number of pixels compared to the number of visibilities.
Well, this is the point.
What you measure are the visibilities, not the pixels.
Yep.
So the pixels are derived from the visibilities.
Pixels are a representation of the visibilities.
But they are not a unique representation, that's the whole point.
So the visibilities are like
Approximations.
are average visibilities.
Yeah, there are interpolations.
Yep.
Interpolations of basically
So
the power you have between different scales.
Just one simple reason is
The size.
the size.
From the computer science point of view, if you had the interferometer has a regular grid, that makes no sense. A regular grid, then it makes no sense. I don't know. I know, but if you have a regular grid, then you can have the fast Fourier transform without any loss of information.
Yeah.
But because of the instrument, we do not have that. Then we are losing information due to interpolation. So yes, we're losing information, and that's why we have all these artifacts that appears in, and then we need something like clean to.
I know you have sparsity algorithm, for example, that are able to represent sparse signal, like this kind of signal, but it's actually not on a regular grid. So I was wondering how. I mean, I understand the data is huge because, of course, you have all the data. So compared to a map where you have been basically reducing. But I really think, well, this is much more powerful if you manage to tame this.
Yeah, but
one of the reasons also is that most objects that you want to look at are compact in images in real space. In Fourier space, they are all over the place. So the information is scattered over all the visibilities if you have a single object. And in real space, it's located in a few pixels. So if you need, for example, to segment your image to make it processable, then all the information will be in just a few segments in images, but not necessarily in visibilities. You have two objectives, they are separated in real space, not in visibilities.
No, but I think for compact sources, it makes sense what you're saying, and actually that's why Clean is working, because it's for compact sources, but I don't think most astronomical objects are compact.
that's why.
But they don't fill your whole field.
Yeah, no.
Generally, sometimes
for sure. And in any case, you won't see them in the information, right? So,
Yeah, but actually, yes, if you try to get extended sources like this one, it's I think you start having a lot of problems due to the fast Fourier transform. Okay. Sorry. Yeah.
When you make the column find, do you succeed to go deeper than other method, and how do you do the cleaning? How do you with the side load?
When I do what? Sorry.
How do you cope with the cleaning, the side load, and do you succeed to go deep, or do you just consider bright sources?
Yeah, that's the new project we are working on that. Yeah, we have a few results, but it's basically showing that we can do better than the fast Fourier transform to this point with certain parameters, which again add more parameters, and we haven't see how clean works over that to this point. Okay, so yeah, this is new stuff. It's not much more.
Yeah, I have two questions actually. One is this is most of the techniques that you show that are basically characterization of data sets,
yeah.
properties of a single data set. So one of the things that we are trying to do actually with the ALMA archive, we are trying to transform essentially the metadata from metadata that are what you know before the observations to actually metadata that describe the content of the observation a posteriori. So a compact representation of what's inside the data so that people can actually search for content and not search for... So one of the things that I was curious is whether you can use your one of the segmentation algorithms, for example, for automatic recognition of lines. We've done this test and if it works. Because this is one of our major headaches that we have. We have different softwares that are trying to do this, but with different assumptions and all of them work.
So yes, you can have like automatic detection of lines, but there is a combinatorial problem that goes beyond this. I have worked on this a little bit, and the problem is that then you have these positions, and then you have to do the cross-matching with Splatalog, for instance. And you need to give certain parameter that, and that's arbitrary. So which is your cross-matching. So you can do it as best as your cross-matching.
Yeah, but in principle, the idea is that in principle you can then use machine learning algorithms to know what type of things you should look based on the type of a priori information on the source. So that would be actually interesting to look into.
Yeah, actually that's a good thing about this representation, that you pass through the other representation in order to produce this very fast. You do not need to make a very complex computation to obtain this. From the representation that it's already more compact than the original cube, you can filter as you want here in order to say with your own criteria which you consider, what do you consider a line. For instance, if it's not more than certain flux, it's not a line. If it's not much for certain delta, the spectral line, it's not a line. It has a gradient more than something, this will be probably another thing. So you can filter over this. And it's probably this number here, well, here is the number of elements. So you can transform this value into a flux. The problem with that is that probably it's not as precise as you can get from the original data, but it's not the point.
If you want
exactly.
Metadata to search, you're not looking for
accuracy. Exactly. So
we should talk about this because I have a follow-up technique. I think that the others are probably not interested. I have another, if I may, which is on the next level. I mean, I think scientifically, what we are now most interested in is not only understanding a single data set, but comparing different patterns in different data sets. And data sets might be theoretical in some cases. So basically,
can be what? Sorry.
Theoretical, numerical simulations,
yeah.
numerical simulation typically. So one of the big problems that we have, for example, in the physics of the stellar medium is trying to match what we observe, the patterns that we observe, with the patterns that are different. And I was wondering whether any of these algorithms could be used to derive some objective measure of these things.
Yeah. It's another of the research lines that we are trying to explore. So the good thing about pushing the fitting on the continuous world as fast as possible is that you will end up with a series of functions, and you have function analysis to help you, and you have information theory to help you. In the pixel level, you also have a little tools to do that, but it cannot help you to do something like accounting for the level of structure that the distribution of the signal has. So you can produce first a simulation, then get this representation, get the real data, get the same representation, and then compare with a metric like the mutual information metric, for instance, the two representations in order to obtain a value that tells you how similar they are. And it will be the value will be similar in terms of structure, not in terms of error, because the error is pixel by pixel, for instance. And if you have your image a little bit disaligned, then the error will start to grow. In this case, as they are continuous functions, you will not have these problems. And that helps you to get a number that is representative of the structure of it. So this is a very interesting research line. From the theoretical point of view of information, for information theory, I have a lot of ideas, but again, the problems here, it's like picking the theoretical model and convert it to something similar to what a telescope observes.
This we can do it for you.
Yeah, but you need the model of the telescope. In the simulation, you also need to have the model of the telescope. If not, you cannot compare, I think. And the other way around, I think it's much more difficult to just picking the real data and try to regress the model of the telescope. It's much more messy, I think. Yes.
Yes, I have a question about the availability on this software, because as I understand you right, I can just take this clump finding algorithm and run it over data cubes, each data cube I have, for example.
Yeah.
Because these are almost all
small
ALMA
ones.
data cubes.
Yeah, ALMA data cubes.
So, for example, I can also prepare a data cube of optical integrated field units, and well, how far can I push this software, this clump finding algorithm, when I'm giving it, for example, a pure emission line spectrum observed, for example, with manga or news?
Yeah, I think that the problem with this software, and I haven't tried because I'm working with ALMA data, is that it might get confused with a lot of non-resolved data. So if you have a lot of stars or functional objects or whatever, and they're not spread, I think the assumptions that I'm making it, they are not the good ones. But in terms of size of what you can put here, I think that the key idea here is that the representation, it does not depend, the size of the representation, the new representation, it does not depend on the size of the image, but on how complex the structure is. So if you have things like this disk, it will have a very small representation compared to this one that is much more complex. It depends on the complexity of what you are doing, the size of the last representation. And that's important also because it will also impact on the time that it takes to represent, if you have something similar.
Are these times calculated on your local computer?
Yeah, in my local computer, not in the supercomputer and nothing else.
Okay.
So it's fast, and I haven't reported any other time because the other times are the times of the clustering algorithms and all that are basically online. You just run it and gives you the result. So the representations are very, very compact. If you have something like 300 megabytes, that it's not so huge for cubes, but it's a reasonable cube. You can end up with a few kilobytes of the compact representation. And you can produce from that a cube that represents things like this, okay? So this is obtained from the representation that we generate the cube of a lot of megabytes and then stack them in order to put it in the slide. But that's the idea that we're trying here. It might be other ways, but we're just trying to represent the complexity of what it's in the image, not the resolution that you have.
Yeah, I mean, with this algorithm, it would be much faster to search, for example, in archives of integrated field units, to search, for example, or when I look around a certain time of emission line and search something like an outlier, this emission line and a velocity outlier to find, for example, gas exhaustion in galaxies, and I think this is quite feasible with this.
Yeah, exactly. That's the major point. If astronomers are not convinced with this kind of representation, no, I want to work with the raw data, like always. You can also use this as part of a service that only helps you to discover data.
Yeah, which can pick
Yeah.
out.
Rather than doing analysis. Yeah, great. It was too. Yeah, you had another question.
Noise is correlated also in the radio, so that's the difference with optical.
Sorry?
Noise is correlated in radio images.
If the noise is correlated.
Noise is correlated, especially correlated in radio images and not in optical images. That's why we can choose X-Tractor, for example, with radio images. But this is for your question. This is why it would be more complicated to use this with the radio data, because the noise has different properties.
Ah, okay, yeah. Because the noise here, you said is correlated because the artifacts of the reconstruction.
Because radio images are pixels are correlated with one.
So we
choose like not optical source fibers in the radio. So if you convert your optical map with the Gaussian, maybe you can use it. It will lose spatial information.
I'm not sure. Well, a student tried this just with infrared emissions, and it works fine. And that's where I saw some problems with not resolved data. But actually, you can just remove that. That is, with a PSR, it's easily to detect a non-resolved object. So. Yeah, this is designed for extended emission. I don't know if we need the noise to be correlated or not, but it's a good question, which is the applicability of this.
I have a question about the number of components that you put in the representation. Is it just chosen analytically until you reach a level of fidelity of your representation, or do you pick it by hand as a user, or?
Yeah, this is a very good question. We have one thing that we control, and the other thing that we estimate. We could control the size of each bubble in terms of flux. Okay, because if we have a lot of time and space to waste, we will do as small as possible each bubble, okay, in order to have more resolution.
So that has a direct influence on the number of components, right? The size of the bubble.
The size of the bubble, and that will impact the number of components that we have. But when we end selecting the components, it's basically on this signal-to-noise ratio estimation. So that's the stopping criteria. So you keep subtracting, if you want, these Gaussians, these little functions, up to the point where the signal-to-noise ratio is in this estimation point. And why this is important? Because if you subtract the signal, or signal plus a little bit of noise, this will be a reasonable number of functions, of points. If you start picking in a cube, you start going into the noise, just noise, the number of elements in the representation will explode. So that's why you need an estimation of the signal-to-noise ratio. In the paper, it said, okay, astronomers are very good on estimating this, but I give this a heuristic that we should revisit and we should work a little bit more because it's very simple. This idea that in some point the signal starts to mix with the noise and we try to detect this point is just an empirical observation that the derivative of this function has a maximum here. But in some point in some data set, then you will have another maximum here. So why you should choose this one and not this one? It's the first maximum. So
also, especially for radio images, the noise it's not uncorrelated.
Yep.
So it depends on the spectral mode. I mean, spatial.
Or if you have
so maybe
a mosaic.
You need to estimate in Fourier space a different wave number. So.
Yeah, and you have some mosaics that have more spectral lines that, more channels than the other, and you have different places where, yeah. And the other thing that we were discussing is a good. This also depends a lot on the good estimation of the RMS of the noise. And for these images, I've just picked, for these data cubes, I've just picked the RMS of the whole thing, which is a very bad estimation, and that's why you have this bad result here. You cannot see here, but you do not have a very good, it's here? Yeah, no, you cannot see. You do not have a very good residual, okay? And that's basically because the RMS is overestimated. So you need to have a good estimation of an RMS and a good estimation of the signal-to-noise ratio. But for my opinion, and that's completely my opinion, that's much more in the astronomy domain that you can understand and set up a good parameter that the things that have Gaussian, the Gauss-Clamp algorithm, which is numbers of iterations after something, or number of fails of the optimization. Things that are not in your domain, it's much more in my domain. So I tried to, in this algorithm, to put everything in the domain that you can sense what the parameter is. Okay? So you have here three parameters, which is RMS, signal-to-noise ratio, and a lambda parameter, which is the amount of the flux that have each element. So with these three values, you can produce different representations. Okay.
So my technical question actually was related to this. So, but in many of our data sets, obviously, even for homogeneous type of sources, the signal to noise and the RMS change on the observation and on the source. Yeah. So one would need an algorithm to use it properly that adapts and essentially searches for signal, trying to optimize also the smoothing of the signal in the spectral domain, for example. Have you looked at this possibility, or you expect this to be done purely?
The RMS, there's a lot of ways to do it, and I think there are some packages. Do you remember which one? The package you told me this morning?
Well, there are several packages, and
yeah, but
Blobcat, for instance,
Blobcat, yeah.
Specific estimation of the RMS.
No, yes, but the point is whether you can adapt to smooth the data in order to pick up a signal that is not, because
this is
more data processing. I mean, pre-processing that you could include in the method.
Yes.
And at some point, it's probably one part of the pipeline if you want to recover the signal.
But
you have to optimize your image.
No, that's right. If you focus on one data set, on one specific science code, I understand. But if you look at the archive perspective, you cannot do that. The archive perspective, you have to have an automatic way of deciding.
That's what I was talking about here. This is adaptive to each data set. It's an heuristic, it's not the best thing that we can do. I think it would be much better. But here, the signal to noise, it's estimated from the same data. Just doing a simple thresholding and an iterative algorithm.
But to answer your question, you can probably decide that if your cut is too low, then you smooth the data. and then you get something which has a better estimate of the same field,
exactly.
probably. So it's just a matter of having touch. Thank you very much. I would like to add 2 or 3 words. So Mauricio will be here to the end of the week to work with us for this inside this Minerva project for signal identification and signal representation in data cube for radioastronomy in general, and ALMA is a particular good test bed for that. Tomorrow we will do a hands-on session at 10 o'clock, Salle du Levant, where we will show his Julia books. So if you have more technical questions and want to see how this plays in real time, you're very welcome to come and discuss that. Otherwise, Mauricio is here in Batimora, 6th floor, so we can come and discuss with him up to Friday. And that's it. There is a newsletter that will use a mailing list for the seminars. If you want to register, if you're interested in this kind of seminar, please register on this list. And otherwise, thank you very much.
Okay. Well, I just want to add that this is just one part of unsupervised learning. I also work on supervised learning, like traditional things. If anyone has worked with that, I'm so open to discuss on any learning thing.